question says that the fuel input per hour of plan 1 and 2 are given us. Fuel 1 has an expression of 0.2 p 1 square plus 40 p1 plus 120 Rs per hour. So that is the amount of fuel that is injected into the boiler. And when you check boiler 2, the fuel expression is 0.25 P2 square plus 30 P2 plus 150 Rp per hour. That is the fuel that is required to be injected into boiler 2 so that this fuel can be converted into steam and turn the steam turbine. But the question is saying that determine the economic operation schedule and the corresponding cost of generation if the maximum and minimum load on each unit is 100 megawatts and 25 megawatts. We are trying to say that if generation 1 can generate a maximum of 100 megawatts, or it should be able to generate 50 megawatts, so it will be able to meet the demand of 120. Then the question is saying that there will not be any transmission losses if the load is equally shared by both units. So if the generation, the load demand, which is 180, is shared amount generator 1 and generator 2. And they therefore ask us that if that happens, what will be the amount of money that is saved for this very generation and the production cost. So in this question, we analyze it in two ways. At the time that the load is not being shared equally, and the time we will see if this 180 maximum demand is also shared equally. What will be the cost involved, the fuel cost for plan 1 to generate to meet demand? What will be the fuel cost for plan 2 to also generate to meet total demand? So let's say this is what we are talking about. In the solution diagram, we can, because it's a thermal generation, we have this as our boiler. Then we have a thermal here, we have a generator here, we have a bus bar. So there's a certain F, that is F1, injecting into the boiler. So this is our boiler, boiler 1. Then this is thermal 1 and G1. This is our bus bar system. Then we have unit 2, that is boiler 2 with its corresponding thermal. Then we have generator 2 here, T2, T1. So they are saying that if this quantity of fuel is required to be into this boiler 1, how much power will be coming out here, the output power here, so that it will be injected into the bus bar. If this is an expression for fuel required for boiler 2, then this fuel is being bent into a steam and turned to the steam turbine. What energy or power will come out from the output? That we call the P2, P1. And they say the load demand, the power demand to run the load is 180 megawatts. The key word there is that they said if there's an equal share of the load, and we are expecting that this generator is rated, the maximum rating is 100 megawatts. That is the maximum rating. And the minimum 2 is 25 megawatts. So it means the generation of this plan 1 should be from 25 to 100, that range. But below 25 or above 100, there is a problem with this plan. Likewise, they have the same equal rating. So mathematically, let's see. If F1, the amount of fuel required for plan 1 equals to 0.2 P1 squared plus 40 P1 plus 120. Let's call equation 1. Then F2 equals to 0.25 P2 squared plus 30 P2 plus 150. Let's call it equation 2. Now, for us to be able to get the amount of fuel that is required, the cost of fuel required to run plant 1 so that it can generate an output to meet the demand. And that means we should use one of the mathematical theory to do some alteration to be able to get a cost. One of the mathematical alteration we'll be using a mathematical theory to do the alteration of this equation to be able to get the amount of fuel cost demand for us to generate, for each plant to generate the required power, so that if the required power is summed up on the bus bar, will meet the total demand is 180. Then let's use the Lagrange mathematical method. Lagrange mathematical method is basically using the differential, integral or differential by part. So we see Lagrange of partial derivative of the Lagrange with respect to power equals to partial derivative of the fuel over the respective power multiplied by the power minus the Lagrange multiplier equals to 0. So this is the formula we want to use. But at this case, since the fuel prices are given, Lagrange multiplier is what? Is equals to 0. So the equation tends to be Lagrange of P equals to differential of fuel over differential of power. Because it said the load is shared equally. So we therefore say that applying this theorem, we can say that differential of fuel 1 with respect to P1 will be equals to 0.2 P1 squared plus 40 P1 plus 120. The partial derivative has a formula that says that constant or coefficient times the exponential function multiplied by the function, then minus 1 from the exponential value. So A is the coefficient, A equals to coefficient, and N equals to the exponential function, the exponential value, or the exponent. And P is what we call the functional variable. Functional variable. So if we will use this very equation as the reference equation for us to be able to alter this, it means that differential of P with respect to P1 will be equals to, this is the coefficient. Coefficient is 0.2. Exponential power here is 2, so multiply by 2. Then P1, 2 minus 1. Then plus 40. The coefficient there is 40. The exponential power is 1, so we don't, so maybe by 1. P1 minus 1. Plus, here coefficient is 0. Then exponential function 2 is 0. Then functional variable 2 is 0. So 120 times the word 0. Then we have df, the P1 should be equals to 0.4 P1 plus 40 as our equation 4. The same theory applies to df2 P2 equals to 0.25 P2 squared plus 30 P2 plus 150 as our equation 2 code. So we apply the differential function to rate, alteration to rate. We have coefficient of 0.25 multiplied by the exponential function value of 2, then 2 minus 1 plus 30 times the exponential value of 1, then P2 1 minus 1. Then this one, coefficient is 150, the exponent is 0. So we have this expression to be 0.5 P2 plus 30. So this gives us equation 5. Now the question says that if the load is shared equally, so it means generator 1 will produce, must make sure that its generation should be equal to the generator 2. Because if the load here is 180, so we're expecting this one to produce around 890. This one should also produce 90. That means the load have shared equally. So that means that the generation of the alternative of generator 1 should be equal to the alternative for what? Generator 2. So we can have an expression like D1 P1 should be equal to dF2 over P2. So we call this one equation 6. But the question says that Paul says that since we generate this, generator 1 generate, or unit 1 generate, unit 2 generate, all of them will be injected into what? The bus bar. And that gives us the total power of 180 megawatt. So it means that the power generated by P1 plus power 2 should be equal to what? 180 megawatt. And that gives us equation 7. So now, we now have two equations. That says that P1, we alterated P1, or differential equation of this, which we have this very equation. So it means 0.4 P1 plus 40 equals to 0.5 P2 plus 30. That gives us what? Our equation 6. But we are just putting in the respective values into the expression. Then P1 plus P2 should be equal to the demand. So now we are now solving these two equations. We can solve these two equations, equation 6 and 7 simultaneously, to be able to get the value for P1 and P2. So solving equation 6 and 7. Equation 6 and 7 simultaneously. To get what? P1 and P2. So can make P1 the subject in equation 6. So making P1 the subject in equation 6. So 0.4 P1 equals to 0.5 P2 plus 30 minus 40. I just sent this one across here. So we have 0.4 P1 to be equals to 0.5 P2 minus 10. So I want P1 alone, so the value goes at 0.4, 0.4. So P1 equals to 0.5 P2 minus 10 all over 0.4. Let's call this one equation 8. So putting equation 8 into equation 7, because they said P1 plus P2 should equal to 180. So now I know my P1 to be equal to 0.5 P2 minus 10 all over 0.4. So whenever I see P1 in the equation 7, then I'll fix it there. P1 plus P2 equals to 180. Now this is P1. And now the other name for P1 is 0.5 P2 minus 10 all over 0.4 plus P2 equals to 180. So I can call this equation 9. Now I can find P2 here by saying that 0.5 5P2 minus 10. This becomes the LCM. This multiplied by this, I have 0.4 P2, then equals to 180 times 0.4. So I can have 0.5 P2 plus 0.4 P2. These are like terms, P2, P2. Then I send this one across. 180 times 0.4. This is negative. Coming here becomes what? Positive. Then this gives me 0.9 P2 equals to, so this and this multiplied by this will give me 72 plus 10. So 0.9 P2 equals to 82. Now I can get my P2 here, divide one side by 0.9, 0.9. So this will give us 91.1 megawatts. So the power generated by plant 2 is now 91.1 megawatts. So let's see how much power will also be generated by plant 1, so that if we merge with plant 2 at the bus bar, we'll be able to meet the demand. So now if P2 equals to 91.1 megawatt power, then P1 plus P2 equals to 180, but P2 equals to 911 megawatt, then it means that wherever we see P1, which is this, we put P2 there. So P1 plus, now P2 is 911 equals to 180. Then P1 will equals to 180 minus 911. Then P1 equals to, so P1 equals to 8.88 megawatt. That is, so this is now the power generated by generator 1 and the power generated by generator 2. At the time that there is no equal share of the 180 load. This one you are just turning on the respective quantity. This is the quantity of fuel inside this boiler. So when this boiler is being boiled without regulation, it will produce an output power of 88.8 megawatts here, and this one will be generating 91.11 megawatt. So you see that at this time there's no equal power generation. Now we want to find out the cost of fuel. The key word is that we need to find out how much fuel will then be boiled into steam so that we can get this power. Because the theory is that for thermal generation, steam is converted into what? Mechanical, and that mechanical energy then converts back to what? Electrical energy to be able to run down the electrical load. So let's see how much will it cost if we want to generate 88.88 megawatts of this quantity of fuel that will be put inside here. We're producing this. Then how much fuel will cost us to generate this? So cost of fuel for plan 1 to generate 88.88 megawatts. Then it means that fuel quantity, which is F1 equals to 0.2 P1 plus 40 P1 plus 120. It means that now we know P1 to be equals to 88.88 megawatt. So wherever we see P1 in equation 1. And we say that F1, the fuel cost for unit 1 to generate 88.8 megawatts. It means that fuel cost equals to F1 cost equals to 0.2 bracket, wherever we see P1, then we put the amount of power there, square, plus 40 bracket 88.88 plus 120. So the fuel cost to generate this power is U, that is RS $5255.15 per hour. So in every hour, this is the amount of the cost of fuel required to be injected into the boiler, so that it will boil to be able to produce this amount of power at the output. Now let's also see the cost of fuel when we are to generate, when plant 2 will generate output of 91.1. Cost of fuel required to generate 91.11 megawatts power. That means that F2, which equals to 0.25 P squared plus 30 P2 plus 150. But now P2 equals to 91.11 megawatts. So what, to get the cost, we just fix in the required power into the fuel cost. So plant 2 fuel cost of fuel to be able to generate this power output becomes 0.25 91.11 squared plus 30 bracket 91.11 plus 150. Then cost of fuel for generating this will be 498.55 RS per hour. So in every hour, this is the cost of fuel, required for us to be able to to generate this. Economically, let's then see if we then divide the respective load into 90 megawatts, because they set at equal share and the load demand is 180. Equal share means that total load demand or total demand divided by the total number of generators that are on. Now we are talking about generator 1 is on, generator 2 is also on. So it means 2 generators are working as of now. So load shared will be equals to, demand is 180 divided by 2. So each generator is expected to generate 90 megawatts. So for us to be able to determine how much energy the industry will save, then if the load is equally shared, it means that P1 now equals to 90 megawatts and P2 also equals to 90 megawatts. So let's see how much it will cost us to be able to generate by 1990. It means that cost of fuel for unit 1 to generate 90 megawatts will be equals to F1 cost, which equals to 0.2 P1 squared plus 40 P1 plus 120. Then cost of fuel for equal generation becomes 0.2 P. Now we know P1 to be 90 because at equal generation, total demand is shared among the two units. So this 90 plus 120. Then cost of fuel for at the time of equal generation will be RH 534 per hour. That is if generator 1 is to generate at 90 megawatts, because the total demand is 180 and there are two plants working. So we share the 180 into two. So each plant requires to generate a megawatts of 90. So let's also see how much unit 2 will be. Cost of unit 2 generating power at equal load of 90 megawatts. So that gives us F2 cost, which equals to 0.25 P2 squared plus 30 P2 plus 150, then it equals to 0.25 90 squared plus 30 90 plus 150. Then fuel cost 2 for unit 2 will be equals to 4,875 per hour. So now this is at equal load generation. So we need to find the total cost of fuel that is being generated during equal load, and the cost of fuel, the total cost of fuel that is being used to generate at the time that each generator is turned on no equal load. So it means that on equal load will be this plus that. Then on no equal load, it will be this value plus this value. Then we then get the difference to see at what load do we save. You've got to realize that when we observe the power, the cost of fuel, when during the time that the generator 2 was generating on no equal load, the value is higher than when the load is shared equally, because this is 4958 point something and this is 487. It means that at equal load, generator 2 costs are what? Reduced, while on equal load to generator 1 load, cost of fuel are what? Increased, and this one what? Decreased. So let's find out the total cost of fuel used during unequal load generation of power. Now equals to fuel 1 plus fuel 2. That equals to F T total cost. That is at the time that this one is generating at a 88.8 mega and 91.1 mega. So we'll be getting a total cost of 5255.13 plus 4958.55. This will be F1 plus F2. This load is at 88.8 unit 1 megawatts and unit 2 at 91.1 megawatts. So let's see what the total value gives us. This will be the total cost. Total cost of fuel for when plan 1 generate when unit 1 generate a power of 88.8 megawatts and unit 2 generate a power of 91.1 megawatts. So let's also see the cost of fuel, the total cost of fuel. When plan 1 is generating at 90 megawatts and plan 2 is generating at 90 megawatts. Total cost of fuel when plan 1 and plan 2 are generating at equal load of 90 megawatts. Since total load demand is 180 mega. So it means that F1 plus F1 prime plus F2 prime equals to RS of 4875 plus 5340. RS 5340. Then that will give us total of R prime 1 plus R prime 2 cost 1521 per hour. So this will be the total cost of fuel that will be used to generate 90 megawatts by unit 1 and 90 megawatts by what? Unit 2. The question is that we should obtain a saving obtained. How much money is being saved during the 2 generation period? If you are generating on no regulation base, you just turn on by just feeding this quantity of fuel into the boiler to convert it into steam, and the steam turn the turbine to generate 88.8 megawatts. And at the time that you are now no more generating at 88 but increased to 90 megawatts, how much cost have you been able to save? So the amount of cost you are able to save during the 2 generation period, that is during the time that you are generating at, on the time you are generating without sharing the load equally, then now you subtract that value from the time you are now generating the load equally. That means that Ft prime minus Ft will give us what? The saving obtained. And that is this value 10251.01 minus this one 10235 165, and that will give us RS 0.56 per hour. So in every hour, if you are generating on equal load, this is the amount of money you'll be able to what? To save. So if you are generating this for a year, then you multiply this by what? 12. That is 12 months made what? A year. So if this is a daily save, then that means that how many days make a year? So we are talking about how many days make a year, then we multiply that days by what? This amount of money. And then it will tell you that economically, if you want to operate thermal generators, depending on the load demand, one, you either choose to share the load equally among the two generation units, and then you operate to be able to what? To save what? More money. But if you are generating on no equal base, realize that this is 88.8 and this is 91. It means that you are stressing this generator more than what? This generator. The cost of fuel required to generate 91.5 is more expensive than the cost of fuel you'll be using to generate 88.8. But if the load is equally shared, the amount of fuel, the cost of fuel here and the cost of fuel here will be what? The same. The difference will not be what? Because if this one is using the same fuel, let's say they are all using oil, natural oil, or they're using coal, the cost of fuel will what? Will be the same. Because the output is saying that, the question is saying that the rating of the output is what? Maximum is 100 megawatts and minimum should be what? 20 megawatts for the rating. Thank you.